Okay, well today we're dealing with heavy timber construction, Chapter 4. So under the building codes we have different types of construction, different fire resistance numbers in Roman numerals from type 1 through type 5. It's type I through V in the Roman numerals. And so IV would be 4, and that's what type heavy timber construction is. So it's more fire resistant than residential construction, which is type V or type 5. But it's also more fire resistant than most types of type 3 construction dealing with structural steel that is not fire protected. So heavy timber, an important factoid, is more fire resistant than unprotected steel construction. So let's move on here. In the olden days, before we had sawmills that could cut up lumber into 2x4s, you could take a tree and turn it into a beam, turn it into a column. You just had to find the right tree that you needed. In modern times, we can cut up the lumber any which way we want, except that we've done such a good job of cutting it up, we don't have a lot of heavy timber left. So heavy timber is very expensive. So most of the heavy timber you're going to deal with is either reclaimed from some old warehouse that's worth more than it was as a warehouse, or it's from engineered lumber, such as glue laminated beams, or laminated veneer lumber, LVLs, or parallel strand lumber, PSLs. Okay, so look at this frame connection. It's a fairly simple frame connection here of these heavy timber members. And this is typically how we connect heavy timber members in modern times in order to make sure that the thing actually is going to stand up and not come down and kill people. We've got to bolt the stuff together with steel connections, steel plates and steel bolts, heavy, heavy bolts. And it's not just thin sheet metal, it's going to be 1/4 inch typically or thicker metal. Here you see what looks like connections without steel. They've even got some mortise and tenon looking plugs that are in there to kind of make it look like this, but those are just caps. Internal, hidden in saw cuts in there, are plates of metal, and then they've got bolts going through, and then they've covered up the bolt heads with those wooden plugs. But again, steel connections, the primary way. And the primary way we make heavy timber rigid is with diagonal bracing. That means a series of triangles like you see in this picture, like you see in that picture, and things like that. And so here is more of a residential scene, and where the only heavy timber here is a couple of beams. You got one beam sitting on top of another beam. And in that case, there's no heavy plates connecting because the structure is rigid in other ways because of the plywood sheathing and everything else in the building. You still got to have a solid connection where that column is sitting on top of that beam is sitting on top of another column. And so these are glue lam beams. Glue laminated beams are what we mostly use for heavy timber in modern times. That's a series of boards, smaller boards that are glued together, and they can splice them and everything else, and so they don't even need long lumber. Here we've got a frame, and you can see again metal plates and bolts that are holding this all together. And the way we make these structures rigid, heavy timber structures, is generally by diagonal bracing, just like you see here with other timbers. And each one of those timbers is able to be pushed on or pulled on, so they can take tension or compression just as well. Here we got a museum that I happened upon, the LeMay Auto Museum in Tacoma, Washington, when I was at a convention many years ago. And I originally come to see the building across the street, the Tacoma Dome that you see on the sign here is over to the right in this picture. And I'll show you that later on. But when I came into this museum, it was pretty neat to see all the cars. They were having a whole bunch of Corsairs when I was there. But anyways, in here, besides the fantastic cars to look at the structure of this thing. they've got glue laminated beams. And so one thing I wanted to point out here is that glue laminated beams are the only kind of lumber that we can really make into curves like this. And nothing else can be done this way, because you can custom make these in that shape with all the small blocks of wood that are joined together here to make glue laminated beams. Here, some more timber that's been bent, and generally that's glue laminated also. And then this one just for fun. So this picture from I guess a fancy house with a vaulted ceiling, I just wanted to point out that when you go and vault a ceiling, you are removing one of the structural elements that's normally there for a house, and that is having ceiling joists running from wall to wall, and that's what keeps the building walls from bulging out from the weight of the rafters. Well, if you use trusses, then you can transfer those loads differently, but when you use rafters, you'd rely on those ceiling joists. And so in here we've got great big heavy timber rafters, and it's even more of a problem. So what happens is that these, in this case, instead of one ridge beam, they've got two, but they are sitting on top of columns, and that's what's taking the weight. And so that's the other way that, or one of the other ways that you can still have an open ceiling and not be in danger of your walls bulging and collapsing. So we'll talk about that more when we get to framing for a house with dimensional lumber, 2x4s, 2x6s, 2x12s. So again, every building is only as strong as its connections, and that's particularly an issue with heavy timber. You've got to make sure the connections are really thought out. Generally, that means having an engineer involved with heavy timber. Your building inspector won't allow you to just do it and then have him sign off, and he won't. They'll expect you to get an engineer to sign off on it, on all your connections and the engineering involved with these beams. There's another case here. We've got a column sitting on top of another column, and then you've also got a shelf kind of made for these two beams to sit on. You've got to make sure that those beams cannot slide off those shelves and fall over, so they've got to be bolted through. I don't see any bolts here yet. They're in the middle of putting it together, I guess. But you also want columns sitting on top of column. If it's sitting on top of the beams instead, if you had those two beams meeting and touching and had that column sitting on top of the beams, then your building would be dimensionally changing, because across the grain the lumber changes a lot more than it will along the length of the log, along the length of the wood. So across the grain, there's more dimensional changes, and so we do not want to ever have a case where you've got a lot of the dimensions of a building being variable because you're sitting lumber on top of horizontal members here as far as the height. These are knee braces, these short little braces, and they are a type of diagonal bracing that does make the building more rigid. But generally speaking, knee braces, unless there's so many of them that collectively they can add up, I suppose. But they are generally not enough of a diagonal brace to make a building rigid by themselves. That said, the other thing on this page, as I'm talking about, is we talk about dimensional lumber, as 2x4s and 2x6s. We refer to the smallest dimension of a 2x4, the least dimension, or the smallest dimension, being the 2-inch number. And of course a 2x4 is really 1.5 inches by 3.5 inches. Well, with heavy timber, generally greater than or equal to 5.5 inches in the least dimension. Anything where the smallest dimension is 5.5 inches or larger, then we consider that to be heavy timber. Here I've got greater than, because in some schools I thought it has to be greater than the 5.5 inch number. Well, then the other thing about this is the nominal number. The 2x4 is the nominal dimension, whereas 1.5 by 3.5 is the actual dimension. So here we're looking at the actual dimension of 5.5 inches. In the building code, and they'll often talk about a nominal dimension of 6 inches for heavy timber or greater. And so that's still, the 5.5 inches is the same thing, because the actual size of a nominal 6-inch dimension in lumber is 5.5 inches. Okay, so Remember, there's three methods of achieving stability of a building: lateral or horizontal, and so diagonal bracing is the first one in this case, and I showed these in chapter 1 when we were looking. But again, with heavy timber, diagonal bracing has always been the principal method for stabilizing heavy timber construction. Laterally, particularly, but even horizontally in times. But you can have floor systems that make things rigid that don't involve heavy timber necessarily, and so but certainly vertically in the walls. So we call it, we call it lateral diagonal bracing. Okay, so now let's look at the fire resistance. I mentioned it a little bit while we were looking at the title page, but fire resistance is a big difference between heavy timber and unprotected steel. Look at this picture here. There is the remnants of a piece of heavy timber that's been burned through so much that what you're seeing, if you see the little spiky things sticking out of that piece of wood, those are the nails. So the timber used to be coming out to the edge of those nails. So it was a much bigger thing. So this wasn't a 30-minute fire. This was a hours-long fire, many hours to burn through. And it's still not bent. It's still not sagging. And it's got the I-beams that were overhead drooping over them. So it just tells you what happens to steel. Steel loses much of its strength at 500 degrees, and the timber is just getting started. So heavy timber lasts much longer than unprotected steel. So that also tells you that all steel buildings, if they're going to be occupied by people and not just a warehouse, they have to be protected from. That means you need a protective coating, protective cover of some kind to keep the steel from ever heating up in the first place during a fire. So when you look at this graph here, down along the bottom scale of the graph, as you go across the bottom, you've got 10 minutes of fire, 20 minutes of fire, 30 and 40 minutes of fire. So let's look at the 10 minutes time and then the 30-minute time. So at 10 minutes, you look up that line and you see the brown curve running across, and at 10 minutes, you've lost maybe 16, 17% of the strength of that heavy timber. And meanwhile, you come down to the gray line at the 10-minute mark, and you've lost about 50% of the strength. 50% of the strength of the steel is gone in the first 10 minutes of a fire. Of this example, anyways, from results from a sample. Now, go over to the 30-minute line, and you see the brown wood line is you've lost 25% of the strength of that heavy timber in 30 minutes of a roaring fire. Meanwhile, so we over-engineer things, so they're generally 4 times stronger than they need to be. So 4 times stronger, you still got 3 times stronger than you need before it fails. Here's what that really means. And so that heavy timber is not collapsing anytime soon. Meanwhile, down below that 30-minute line for steel on the gray line, you're seeing we've lost 90% of the strength. So this is how the Twin Towers failed. We had a fire, and as that fire kept burning with that hot air jet fuel, eventually a floor failed and it's typically the connections that cause the failure. So when the connections got heated enough for a whole floor to fail, it collapsed. And then it acted like a giant pile driver, shearing off floors after that, because nothing would be made strong enough to take the whole weight of a building dropping 15 feet to the next level. So this is what we have to do with steel, is to protect it. But it tells you, again, just how heavy timber, including glue laminated beams, how well they can do in a fire. And that's why we can still use heavy timber in public buildings, assembly buildings like theaters and churches and places where we want to have some warm materials and still not have to worry about it. But it has to be open. It can't be hidden. Okay, so let's look. There's the same picture up closer, but you can see those nails. They were whatever they were attached, I don't know what was going on there, but what was going on this thing as far as cover and all those nails in there. But the point is that tells you something about the dimensions of the original lumber. Here's a test case. It's a little blurry, but it's showing you they took a glulam beam on the left, and then they had a steel I-beam on the right. And the glulam beam, even though they laid it over inside, it's still not drooping. And the steel beam is just wasted, destroyed. So let's look at heavy timber construction. Again, it's type IV, and oftentimes it's written with HT beside it, which stands for heavy timber. So when you're looking at heavy timber and type 3B for certain, and even with type 3A, in a lot of those cases, the numbers are higher for heavy timber construction of the number of square feet per floor, the number of floors, everything. So type 4 construction, IV, is better than type 3 construction when it comes to fire resistance. So type 3 construction is what we typically build warehouses out of. They're not going to be occupied. Well, especially type 3B. Type 3A could have an office as part of it. And so then, but generally that portion of the building would still have to come under fire protection. And so a lot of warehouses, you have an office up front. Okay, so there's that. And this, of course, type 4 construction is still better than what we do with residential construction with dimensional framing with 2x4s, 2x6s, 2x12s, etc. Okay, so let's skip along. This picture is showing you an old-fashioned heavy timber construction in a three-dimensional rendering. And you see these girders that are running across. And you see beams sitting on top of those girders. Well, just point out that a beam and a girder, they're both beams. It's just a girder is a big honking beam, whereas a beam would be a regular size. So those terms can change depending on the project. So generally, the very largest beams in your project will be called girders, and then the other ones will be beams. And sometimes when you got a whole bunch of beams together, kind of like we do, they could have called these floor joists actually, but they're heavy timber, so they've called them beams. But in construction, when we have a bunch of beams that are sitting on top of a girder, they could also be called joists. But generally, it just depends on there's some of these terms. But there's a lot of names for beams. Headers are beams, but their headers are contained within a wall going around a window or a door to transfer the loads around the window or the door. Okay, so the key thing I wanted to point out here is that the column is not sitting on top of a beam. It's important that the upper column is not sitting on top of the beams. It's connected to the other column through some notches through and holes through the two beams that are as they meet. And that thing is called a pintle. In this case, it's a cast iron pintle. So let me just kind of go to the next page where I'm zooming in on that cast iron pintle. And so you need to be able to recognize, if I ask you, what do you connect one column, what do we use to connect columns through floor frames to other columns? We use pintles. So that term is an important one. But this is what you're looking at. That's a pintle. And here's another version of the pintle right here. The other thing to remember is, again, those two beams, when they're sitting on top of that column, they have to be kept from sliding off the top of that column, or else everything goes wrong. The building collapses. So they have to be tied. In this case, they had these dogs. They're kind of U-shaped, very extended U-shaped bars that are bent at each end to stick down into slots. Nowadays, you would never do that. You'd use bolts going through metal brackets. So again, this is an old picture of an old building. But again, the cross-grain shrinkage could lead to differential settling and differential tearing apart of siding and everything, all kinds of things within the building. So you don't want a column sitting on top of a column, on top of a beam. You always want column-to-column connections. Okay, so here we've got a column that's running straight through, and they've built a shelf on each side with some chunks of wood, and they've bolted that through, and that makes a shelf. The building code says that you have to have at least 1.5 inches of bearing surface. So this is at least 1.5 inches material that these beams are sitting on. But to keep them from sliding off their shelves, their little shelf on each end, they've got that metal plate that may be 1.5 inches or something like that thick or wide, and maybe 1/4 inch thick plate on each side, bolted through with nuts and bolts and washers, and that's keeping those together. But meanwhile, notice the split rings. I talked about split rings back in chapter 3 in wood when we were talking about the fasteners for wood. The split rings are used a lot by the train trestle structures when they're building the little bridges out of heavy timber. They've been doing that for 100 years like this with split rings, because they could auger out and put that spring steel metal circle in there between, to fit halfway between one piece of wood and the other, and then you can bolt through and hold it all together. It makes a very strong connection. Another thing you need to be aware of is the terminology about fire cut beams. So a fire cut beam is one that's been cut at a tapered angle, something less than 90 degrees. So on the left-hand picture, you see a 90-degree cut, and you can see how it's catching the top of the beam pocket where the beam is sitting in. It can act like a giant crowbar and tear apart that wall and maybe kill firefighters during the fire if the beam was to burn through. Whereas by taper cutting it, it clears the pocket. So that's sometimes used. That's a technique. The other thing you can do is just make the beam pocket bigger. So that's typically in modern times what we do. But fire cut beam ends, remember, you're tapering the end clear at the top so that it clears the top of the beam pocket, basically. So here we're looking at a beam sitting on a concrete wall instead of a brick wall. Concrete's stronger than the brick or the block wall would be, but they still have a similar problem in that moisture can wick up into the wood. If you sit a heavy wooden beam, just sit it on a ledge. For masonry and concrete, you have to have at least 3 inches bearing, whereas if you have wood sitting on steel or wood sitting on wood, you only need to have 1.5 inches of bearing surface. So the last 3 inches of this beam has to be sitting in that directly on the concrete. When I say directly, but not completely directly, it'll be sitting on that bearing plate. But they still require 3 inches of this stuff. So that said, so it's not touching the concrete because of the bearing plate, and then you should have at least a 1/2 inch clearance on all sides of that beam. If it's in a beam pocket, then it needs to be 1/2 inch on each side and the end on all sides. And so that helps it to clear the pocket, but it also helps with the ventilation so that no moisture is going to end up transferring to the wood, or as it's happening, it's drying out. It's a safety for the moisture. The other thing to point out is when you connect a beam, you connect it at one point at the bottom. You don't connect it at the top too. You think, oh, well, it'll be stronger. Yeah, but there'll be bouncing and deflection on that beam. No matter what kind of beam, there's always some deflection. And so we connect beams in one place, not 2 places. So in this case, down at the bottom, very, very common place to have it connected. And it's not going to be connected to the top. But you can do a stabilization thing like this clip angle that's fitting in here that's keeping it from rotating. Beams and trusses are only strong in one direction, so they have to be kept vertical. And so we do various things to keep the beams vertical in various kinds of bracing. Okay, and then if your joists are far apart, then you might need something thicker. With a 2x12 framing for a series of floor joists, they're going to be for house construction, residential construction. You'll have those joists will be only 16 inches apart, 16 inches on center. Well, then you can get away with 3/4 inch plywood. But if you've got your joists 2 feet apart in heavy timber construction, or maybe 3 feet apart, you're going to have much heavier decking to span those distances. So that's really what this is, different techniques of joining your decking. If it's not plywood, then it would be something like this. But a lot of times now we have very strong plywood that's particle board treated particle board to try to keep it from moisture problems, but they could be 2¼ inches thick. Very heavy stuff. Can span greater distances. One thing about heavy timber, it has to stay open. You cannot have a drop ceiling, a suspended ceiling covering it up. So it has to remain open. So it says here, fire-resistant heavy timber floors and roofs must be constructed without concealed cavities where fire could develop undetected. So that's an important rule with heavy timber. It has to be open. That means all your building services, electrical and plumbing lines and sprinkler line, everything has to be laid out nice so it looks nice, or because it's not going to be hidden. Remember that the bracing is done by diagonal braces. So here's an example where they've got a whole bunch of knee braces. There's so many of them that collectively it does add up to something. Although I bet you this building still moves around. It's still not enough. Because those knee braces, unless they're fastened with steel connections, they haven't got a hope of being strong enough. You know, a lot of times when you change the use of your building, if it was a warehouse, you didn't have to come under as strict of standards because there's no people in there, or hardly any people in a warehouse. So the numbers of people, the risk is down. Whereas if you could take that warehouse and decide you're going to convert it to lofts, apartments, or if you're going to change it to a restaurant or something, it's going to come under a whole different usage, which brings under a whole different set of building codes. And so then you may have to retrofit. And that's what's going on here. In this case, it's for earthquake, where they've put in these heavy steel members to brace this building and keep it rigid. In this case, maybe it's for occupancy. So the problem here is that you got to brace these walls for earthquakes, and also in Louisiana, we don't have the earthquakes, but we have the wind, and the wind can blow these things over. So you got to. This building is only as strong as its connections, and so they had to beef up the connections from this wall system to this floor system with the steel angle iron and the bolts going through to connect that. So you can connect that wall to that floor system with those metal straps that are going onto that OSB that they put down on top of maybe the other flooring to have a positive connection. And again, no concealed cavities. So all this stuff has to be made nice and pretty if you want it to be, if it's going to be a public place so that the building services have to be made out in the open. So they're going to have to be looking pretty good. Okay. The connections. The connections, I've said, are the most important part of a building. So let's look here. So in the old-fashioned construction, they'd have mortise and tenon joinery where they kind of do a bunch of woodworking, craftsmanship to go and build these strong connections. Well, the problem is they're just not something that an engineer can quantify to just tell you how strong, because it all relied on the skill of the craftsperson to do. So, and then they'll peg connection, a peg going through to kind of hold the mortise and tenon. Well, that wood can get sheared off pretty easily. So it's just not a strong enough connection. And that's what I've been talking about these knee braces for. So in modern times, we have to have metal. There has to be steel involved. And so you can have it concealed like this, where you have metal plates going through saw cuts in both pieces of wood, and then you run the screws through it. In this case, the metal plates actually didn't have holes in them. They have self-tapping, really good self-tapping screws. They're pretty expensive. They're about 1/4 inch screws, and they screw them through this material in this pattern. But this is more common. What you see on the left is the most common thing, where you have a customized bracket meant for that particular case, and of steel with straps on both sides where the bolts can drill through, and be nuts and bolts and washers to hold all this together. So the washers are really important, especially in the cases in this picture where you don't see it going through a metal plate, because you distribute that load. If otherwise that bolt head could suck through, or can be pulled through the wood at least somewhat. And so, the washer's not just any washer, but the right thickness of washer. The bolts have to be of the right strength, the right size, and such, all engineered by a structural engineer. This is how we connect heavy timber. So you just can't go do heavy timber on your own without engineering, because it's not specified in a way that you can use it that way in the building codes. Everything, the building inspector will require you to have an engineer just for that. Even with a house, where you don't generally, in Louisiana, you don't need a lot of engineering for a house, because there's no snow loads on the roofs, and there's no basements, and those are the two areas that generally need engineering and residential construction everywhere else. But if you decide you're putting heavy timber in your room, that the building inspector says, yeah, but you're going to have an engineer sign off on that part, and they'll basically figure out what size of connection, and then the complication is connecting from one kind of material to another. Heavy timber still requires special connections to other kinds of wood, but if you've got a steel beam in there instead, then that changes everything, and you definitely need an engineer to sign off on how that material is being connected. Okay, and here's another connection here of a tie rod, and it's got a huge bunch of plates and bolts that are putting this through, so it's a very strong connection. But a tie rod is like a rope. You have to treat it like a rope. It only can be pulled on. Yeah, it would be able to take some pushing before it would buckle, but so in every case we have tie rods, we have a pair of them, because you'll have to have another one going the other direction. So I see two tie rods in this picture, but they're both going the same direction. So that means there's got to be another pair going another direction somewhere else in this picture, because you can't push on a rope, and you have to treat tie rods like as if they are ropes. This must have been an old building of wood that they've added a steel building to on the back end. Copper sheeting and stainless steel sheeting can be used as flashing against moisture, and it's pretty durable. As you see, even this wood is not faring very well on the right-hand side of this page. In Louisiana, you'd need something more. So, longer spans in heavy timber, well, glulam beams are your choice in modern times. If they're curved, it's the only material really that we can curve. So if I ask you a question about which kind of engineered lumber or what kind of material could be used for a curved arch shape, it would likely have to be glue laminated beams. And that's what we've got here in this hockey rink. They easily can span 80 feet and more. It's all a matter of how big a size and the economics of the whole thing. Then you can take heavy timber and convert them into trusses, use them as giant heavy trusses, and they can span a couple 100 feet. This is way beyond anything we normally do with dimensional lumber like 2x12s. You're lucky if you can do 20 or 25 feet with a heavy timber for a carport roof line and such. Then we can build rigid frames where you've got the walls and the roof all together as a frame like they're doing here on the left, or on the right it looks like they're building kind of a steeple or something in this case. Maybe in the back they've got, maybe it's the same building actually now that I look at it. Yeah, it might be. And and then the very longest span in the world is in Tacoma, Washington, in Washington State, and that's called the Tacoma Dome. It was, as you see, it was built in 1983, and the span is 530 feet. Now we have stadiums and domes that span much greater distances than that nowadays, but for wood, this is a record, and it remains the record. So here we are inside that dome, and you can see it's a pretty big place. It rivals some other stadiums we have around here, and but made of wood as a wood span, and that's what makes it spectacular. 530-foot span is pretty amazing with wood, and they were doing it as a statement because lumber is their big industry around there. So here it is on the outside. You can't see the heavy timber in here, but again, that's across the street from the other museum that I was showing you earlier with the glulam beams that were U-shaped. So, beyond that, all I've got here is some links that are useful. You know, you've got a 1,200-word essay to write for this course before this course comes to an end, in the last couple of weeks before this course ends. And so you're going to need to start thinking about what your essay is going to be about. You get to choose your topic. Anything related to construction materials and or methods. And so heavy timber would be a great topic. And so I've got a bunch of links in here. I just want you to start thinking about that. You also have an outline that's due well before then, just before exam number 2. Exam number 2 comes up, and just the week before that, or the week of the exam, you've got an essay outline to submit. And I'm just asking you to give me one page, give me your breakdown of how you're going to write this topic, what topic you're going to pick, and what you are going to write about, how you're going to break down your topics. So that's enough about heavy timber for today.